You can understand this sort of also, well, the numbers are kind of interesting because it shows that the baryon chemical potential should be the order of the nucleon mass when this transition occurs. So it should be occurring at a relatively low baryon density to quark ionic matter. But the transition to quark gluon plasma can happen at a larger scale. Now, of course, in the real world, the square root of NC on this plot is more like about 1.6 or something like that. So the separation in scales isn't so large. But later we'll see some quantities where the factors of NC are huge, like NC cubed. And that means it can be a very, very large effect in that circumstance due to the large NC limit. Next slide. Okay, so how do we think about another property, which is chiral symmetry? Well, chiral symmetry is tricky because there are general arguments that chiral symmetry should be broken if the matter is confined. But there are many model calculations which calculate the effects of chiral symmetry restoration, and they show chiral symmetry restoration should occur at a relatively low energy density. And in fact, what happens in quark ionic matter is kind of amusing, because if you assume that the chiral condensate is translationally invariant, then of course you will find that this region, intermediate region, the chiral condensate is excluded and chiral symmetry is restored. But it turns out that when you allow the system to have inhomogeneous regions, inhomogeneous regions allow the chiral symmetry to be broken in a translationally non-invariant way. So strictly speaking, this intermediate region has chiral symmetry broken, but it's broken in quite a strange way. And this is something which people have tried to understand, and there are various models of it, and it's generally pretty much believed that in this intermediate region there are inhomogeneous condensates, but the exact details of what the nature of these condensates are not really understood. Next slide. Okay, now you have to ask the question. Okay, this is the big question associated with the neutron star data. How can the density stay fixed if the Fermi momentum goes up? Well, there's a way to make that work, okay? You see, if the Fermi momentum goes up, the nucleons are generating very, very high densities. It goes like K Fermi cubed. See, we think that the baryon density has to go up enormously. But for a moment, suppose you put the nucleons on a shell of varying thickness as the density increases. That is, the baryons were not sitting on a shell between a large K Fermi and K Fermi minus delta K. And then in that region, you could tune the thickness of the shell, make the shell thinner and thinner as the Fermi momentum goes up, so that the contribution of baryons is small. So you can solve the problem of baryons by requiring that all the baryons are on some shell. And however, the quarks can inside that Fermi distribution, you expect that there are going to be quark degrees of freedom. Why? Because you have to have filled Fermi Cs, and the filled Fermi C, the only thing left to fill that Fermi C are the quarks. But the quark chemical potential is the order of mu b over NC. So you see, when mu b as mu b is becoming large, mu q is actually fairly small, okay? Because you start off with mu b's deviation from free kinetic energies, which is small, and then what will happen is as mu b goes up, it becomes 0.1 times 1.1 times the mass of the nucleon. Then mu q will be equal to the mass of the quark times 0.1 divided by NC, and that'll be small. So what happens is that the Fermi momentum associated with quarks is of order 1 over NC times that of the nucleons. The nucleons start off at lambda QCD, therefore the quarks start off at very small Fermi momentum, and by the time the nucleons become relativistic, that's when the mu quark becomes of order lambda QCD, K quark becomes of order lambda QCD, And when K quark becomes of order lambda QCD, that's when the density of quarks becomes of the order of the density of nuclear matter. So you see, you can solve this because on the shell, the nucleons are sitting, it's getting thinner and thinner. The density of nucleons gets stuck at some value, and then you start to fill up a sea of quarks. But at first, because the Fermi momentum of the quarks is so small compared to the Fermi momentum of the nucleons, it makes only a little effect on the density. So the density has to become large for the quarks before it ever makes a significant contribution to the energy density. So that's kind of very, very amusing. The hypothesis of quark-ionic matter, I've never made any use of a phase transition. It's also true that this quark-ionic transition requires a transition with varying energy as close to the nucleon mass that we saw in the previous slide. So the transition may, in principle, occur quite close to nuclear matter density. Next slide. Here's the picture I wanted to show you. So the picture of quark-ionic matter are nucleons on a Fermi surface, and as you make the radius of that Fermi sphere larger and larger, that shell becomes thinner and thinner, so that the density of nucleons on the surface stays roughly constant. And at first, when you begin to fill up the shell, the Fermi sphere of quarks in the interior, when you begin to fill that up, it doesn't make much contribution to the density. So you see, you can increase the Fermi momentum quite dramatically without changing the density very much. That's the whole trick to this whole story. Okay, so what happened here? Oh, just a second. Are you still seeing me?
Yes.
Okay, good. So let's go. Next slide. Yep. So this is the last slide, and this shows all of this stuff mathematically. Basically, if you express the density of baryons in terms of the Fermi momentum of nucleons, it goes like K Fermi cubed. If you express the density of quarks in terms of the Fermi momentum of quarks, it goes like K Fermi cubed. I don't understand what's happening with Firefox or anything. Okay. Something's happening to me which I don't like. Okay. So the density of baryons goes like, just a second, I want to do something here. The density of baryons goes like, what the hell is going on? My system has run out of application and everything. Okay, the density is the order 1 in powers of NC okay. The density of baryons in terms of the Fermi momentum of nucleons is the order 1 times K Fermi cubed. The density of quarks in baryons goes like the Fermi momentum cubed to the quarks, okay? So for the Fermi momentum of the quark of order lambda QCD and the Fermi momentum of the nucleons of order lambda QCD, they both become roughly of the same order of magnitude, which is the density of nuclear matter. You see where the problem is at, is that the Fermi momentum of nucleons is NC times the Fermi momentum of quarks. And because of that, when the Fermi momentum of nucleons is the order lambda QCD, the contributions to quarks is tiny. And only when the Fermi momentum of the nucleons becomes of the order of the mass of the nucleon, and the density of baryons would naively be very, very high, does the density of baryons and quarks become of order lambda cubed QCD. So this does what we want. It says that if you put the nucleons in a shell, you can make the baryon density of the nucleons small, and then as you do that, the baryon density of quarks will turn on. You can also calculate the energy density of baryons in this way too. And the energy density variance turns out to be the number of nucleons times lambda, mass of the nucleon times lambda QQCD. And the energy density quartz has a density of quartz in it because it depends on all the quartz. That has an extra factor of NC, and you see the energy density variance and energy density of quartz is roughly the same when the baryon densities are the same. However, you can see that the pressure jumps dramatically because for a non-relativistic gas, the pressure is suppressed by a factor of Kf over Mp, while the pressure, on the other hand, must jump by a factor of the energy density of quartz. So there's a factor of order NC, which is involved in this. So what I tried to explain to you is just very, very naturally in a large NC limit by making the assumption that the nucleons go into shell and the quartz sit in a filled Fermi seed, you can get the properties you need of having a very hard equation state. And this is precisely what you need to explain the properties of nuclear relativity. Next slide. Okay. Uh-oh. Are you there?
Yeah.
Oh. Okay, so somehow I've lost my connections, but I'm still there. So on the left, can you hear me? Okay. So the last slide is what I like to do when I'm doing something which honors the person. I like to add a poem at the end. And this is a nice poem, I think, by Robert Frost. It's a fairly well-known poem. And it goes stopping by woods on a snowy evening by Robert Frost. Whose woods these are, I think I know. His house is in the village though. He will not see me stopping here to watch his woods fill up with snow. My little horse must think it queer.
Yes, he is not audible. Yes. Yeah, yes.